The next application of Gauss law, which we are going to discuss, is for an infinite line of charge carrying charge density rho L coulomb per meter. We'll consider a straight line of charge which is infinitely long. For this infinite line of charge, the flux lines are going to be directed radially outward throughout the entire length of the line. We can consider a cylindrical system, and the flux density vector D has the component A rho. Throughout the length of the line, the flux lines are radially outward. For such field distribution, the closed Gaussian surface can be chosen in the form of a cylinder of radius rho and height L to satisfy the two conditions. Everywhere on the surface, D should be tangential or normal, and everywhere on the surface, D should be constant. When we look at this closed Gaussian surface in the form of cylinder, the number of open surfaces which forms this closed surface are 3 in number. One is the top circular disk, second one is the bottom circular disk, and the third one is the lateral or curved surface of the cylinder. For the top and bottom circular disk, the flux density lines are tangential, and for the curved surface, the flux density lines cut the curved surface and leave out. Also, on the curved surface, radius is constant, thereby D is constant. So this choice of closed Gaussian surface in the form of cylinder satisfies the two conditions as per the Gauss law's characteristics. Now, we should estimate the charge enclosed in the right-hand side, which can be estimated by performing integration of this line charge density throughout the length of this Gaussian cylinder. So integrating rho L over the length of the Gaussian cylinder will get charge enclosed as rho L times length of the cylinder. And we have to estimate the left-hand side by performing integrations over the three sides, which are top circular disk, bottom circular disk, and the lateral surface of the cylinder. In the top and bottom, vector D runs tangential. We know if D is tangential, then the area element and D are at 90 degree, and D dot ds become 0. Now for the curved surface of the cylinder, D cuts the surface and goes out, which gives the maximum value of D dot ds, and D is also constant in that curved surface of the cylinder. We should now estimate D dot ds for the curved surface of the cylinder, where radius is constant, angle phi takes the range 0 to 2 pi, and the height takes the range 0 to L with variable elements as phi and z. The area element for variable phi and z is rho d phi dz in arrow direction, and d vector is also in rho direction. Dot product of d and ds gives the integrand of the left-hand side, which is d rho d phi dz. Now this has to be integrated over the entire range of phi and z of this curved surface, which gives d as constant, and the integration is for phi and z, giving 2 pi rho L times d rho, and this 2 pi rho L is the curved surface area of this lateral side of the cylinder. Now this has to be equated to the charge enclosed, and thereby we'll get the unknown d on the surface of the cylinder. Equating the two, we'll get the rho component of flux density on the surface as rho L by 2 pi rho, which is directed in arrow cap, gives the expression for electric flux density due to infinite line charge. From this, we can find the electric field intensity as d over epsilon, thereby giving the expression for electric field due to infinite line charge as rho L by 2 pi epsilon rho arrow cap.